Live from LaGuardia Community College, Dr. Joshua Tan.
Well, thanks very much for having me. As was introduced, my name is Joshua Tan. I'm a faculty at LaGuardia Community College, which is part of the City University of New York. We have an astronomy group that works through the entire CUNY system, and we meet at the American Museum of Natural History. So that's where I do all of my research, and then the teaching is done at LaGuardia Community College, as well as the Graduate Center and all the other parts. It's a wonderful group. If you ever come down to the American Museum of Natural History, let us know, and we'll wave hello, and you can see where all of the research happens, which is pretty exciting. It's right next to the big sphere where the planetarium is. There's little offices in the back, special elevators that only staff can go up, and then we do all of our hard work there. So I was, before at CUNY, I was actually at Pontificia Universidad Católica de Chile in Santiago for 3 years as a fellow there. And when I was hired by CUNY, I was told that I was hired to teach the class Life in the Universe. It is a class that they teach at LaGuardia. It's sort of a unique class. There's 250 students that take it every single semester. It's one of the most popular classes they've ever had. And it just keeps getting more and more popular. So it was pretty exciting, although when I first heard that that was what I was going to be teaching, I was like, well, yes, Earth, what more can we say? Let's sit down. That's it. There's your class. Thanks for coming. But yeah, there is a lot to discuss here in terms of speculation, in terms of ideas, and so that's what I hope to give you today. It's roughly about content from about the first 4 classes that I run. And I just actually taught one today, so I'm fresh off of that. And I'm going to try to give you the flavor of this, and I actually literally mean flavor. I'm going to use an extended metaphor. Well, you'll come to see what it looks like. But we'll start off right now. This is what I start all of my classes with. It's a huge discussion as to what the definition of life is. Has anyone ever Googled this before? What the definition of life is? Yeah.
Let's get a Monty Python reference.
Did you come across this list?
Oh boy.
Perhaps? Did you come across this list?
Yep.
Or similar sorts of lists, perhaps in your studies at some point. This is usually what is touted out in the textbooks. This is the definition of life, and then they explain each of the following things, right? Life must be organized. Okay, fair enough. It has to have metabolism. As far as I can tell, this is the biological equivalent of energy production. That's what it means, right? How do you interact with energy? Do you transform energy into one form or another? The next one is another biological term that I basically think means stay the same. Homeostasis, right? But stay the same is a nicer term, I would say. Growth, I think we can all, understand that. Reproduction, also really easy to understand term, at least, you make copies of something. Response, this usually comes along with stimulus. And then evolution, things change over time. This seems like a reasonable list to us, but it's a problem. What is the problem? Does anyone see the problem with this list? Yeah? What do you learn?
Computer virus satisfies them.
Computer virus satisfies all of them. Fantastic. And other problems?
We have a sample size of 1.
Well, perhaps, although, that's at least not 0, right? That's better. Better than 1. But I think this is a problem that a computer virus might solve this. In fact, I usually propose another object that solves all of this, and that's this object, which we saw a picture of today. Well, let's verify that this is the case, right? So this is a star, well, our star, but it's a star anyway. Is it organized? Well, yeah. If you look at a star, it has different layers, right? There's the core, there's the radiative envelope, the convective envelope, and so on and so forth all the way out. That's an organization, if I've ever heard of one, so I'm happy that it's organized. Does it have a metabolism? Well, it certainly produces energy, right? Nuclear fusion is the source of energy for a star, so maybe it's not the metabolism you and I love, but it's certainly a form of energy production and transformation. So, okay, we'll give it metabolism. How about homeostasis? Well, just like the biologists, the astrophysicists have their own ridiculously long word for staying the same. In the context of a star, it's called hydrostatic equilibrium, right? The same idea, though. Things stay the same. You try to, collapse down with gravity, and it gets forced back out with pressure. That's the idea. So, homeostasis, we got that. How about growth? Do stars grow? Well, they're not growing so much right now, but neither are a lot of the people in this room, or at least not in the ways we might like. The idea of growth is something that may happen at a part of the life cycle of an object and maybe not later on. And certainly stars grow when they are first born by accretion, the process of bringing things in. So sure, they grow. At some point in their life, they grow. What about reproduction? This one usually stumps some of the less savvy students. But absolutely, stars reproduce. How does it happen? Well, it depends on what kind of star you are. But in general, most stars towards the end of their lives give off a certain amount of material that then goes out to seed other material constituents in the interstellar medium, forming new stars. And at the most dramatic, they'll explode and send out shock waves, which can then collapse gas somewhere else and then form another new star, sort of almost directly. So this is not the type of reproduction we may be used to, but it certainly is a form. Stars tend to cause other stars to exist nearby, and that's as much of reproduction as we can hope for, making copies of themselves. How about stimulus and response? Absolutely. We may call it gravity, but it's still the same thing, right? Stars interact with other stars in binary orbits and so forth. And finally, evolution. Well, there's an entire subject. You can spend your life studying stellar evolution. So absolutely, they evolve. So are stars alive? Silence. This is what happens. Well, we kind of think they are not. And why is it that we think that stars are not alive? That's sort of the first question that I'd like to. And when we come to an answer to this, we may come up with some understanding of how we would go about looking for things we think of as life, rather than saying, all right, stars, computer viruses, we're just going to be really broad-minded about this, which is another approach. You can take that approach. But we're going to try to take an approach that might be a little bit more tied to the biology, the biological sciences that are happening, also chemistry. It's a sort of an interdisciplinary field, this new field of astrobiology. So why isn't a star alive? Well, the star is not alive because it doesn't do these things. It does these things, but not with this stuff. What are these things? Well, this is a protein. And proteins are pretty important to living things. You would not do so well if you didn't have them. In fact, there's very little that we can point to that we would be certain is alive that couldn't do what they wanted to do with proteins. So that's an important chemical to keep in mind as something that's important for life. But perhaps even more dramatically important for life is this chemical, which you may recognize as DNA, but we might be a little bit more broad-minded and just say nucleic acids. DNA is deoxyribonucleic acid, but we could also include RNA. There's a big controversy as to whether viruses are alive or not. I'm inclined to say they are, and part of the reason I'm inclined to say they are is because they do interact in sort of the same way with all of these things. They just happen to use, well, proteins and RNA for the most part. Some of them have DNA as well, to do these things. So when we define life in the context of the class that I teach, and also in general in astrobiology, we usually say life does all these things through the processes of these chemicals, as opposed to, well, nuclear fusion in stars or computer code, right? These are the different things. Maybe in some other philosophy and justification, we can come up with a different definition, but this is what we're going to confine ourselves to, and you'll have to argue with me afterwards if you don't like that idea. But that's what I'm going to start with. I'm going to start with this definition, this mess. That's what we're going to call life. And hopefully you go along on the ride with me. All right, so this is where my extended metaphor starts. I want to invent or develop or have some life with some protein and with some nucleic acids, maybe one or the both. And that's the sort of general thing I'm looking for. This was something that people have known that they wanted to do for more than 50 years now. And the first famous experiment that went on to try to demonstrate that you could perhaps create things that would involve the things that we said needed to be living in the chemicals that we were describing was this experiment done. We named them after the last names of the two gentlemen that did it. This is the millerurey experiment. And this is the setup. Actually, if you see a picture of it, it looks remarkably like this. The idea was to try to replicate what the conditions were like on the primordial Earth, which was hot and which was not particularly pleasant. There wasn't the atmosphere constituents we have today. In fact, the atmosphere constituents they thought we had in the primordial Earth turned out to be not correct. So the things that they included are not exactly the right ones, but it's the concept that is there. And in fact, subsequent to that, we have done other experiments that are similar that have resulted in the same results. And the results essentially are that if you have the atmosphere of primordial like Earth, if you have a water source and a heat source, and you have some sort of water cycle, which is what happens here on the Earth, eventually, given enough time, it doesn't take that much time actually, you will produce chemicals that are very similar to the ones we said we needed for life. In particular, this particular experiment produced amino acids. Amino acids are the building blocks for proteins. And so that was a remarkable experiment, and it continues to be replicated. It's one of the first things that we've started to think about and how we would make life out of chemicals. What would we need to do? Something along these lines. So that's our recipe. But subsequent to that, we've become a little bit more sophisticated in our recipes. And this is one of the newer recipes that you may have heard. This is the RNA world recipe for creating life. The idea here is that you start out with nucleic acids, RNA in particular, in this sort of mess of the early Earth with the water and the nucleic acids all mixed together. And it turns out that the activity of RNA is such that you can start doing some really interesting things. RNA will fold much like proteins fold and form things that look like enzymes. Enzymes are the sort of magic that proteins give us. But RNA is not a protein. It has a lot of the same characteristics that we now use in our own bodies and our own life cycles for proteins. RNA will do it sort of on its own if it's in isolation. In fact, there are entire research groups that spend all their time putting different amounts of RNA together, mixing it up, and seeing what comes out. It's sort of amazing what you can end up with. And this is the basic hypothesis, not confirmed, but still an interesting recipe idea. You start off with some RNA, it starts to fold up, forms different sorts of complexes. Eventually, evolution takes hold. The best things end up surviving. And eventually, you have these things, they don't even call it life. They call it proto-life, things that start to behave like life. This might be the explanation for how life comes from things that aren't alive. This is the recipe. But we're interested in astronomy, right? So here I have a recipe. What do you need in order to do this recipe? What do you need? Well, you need ingredients, right? So what are the ingredients? I have a nice picture of ingredients here. This is a nice freely available picture. This is the primordial soup, right, of the early Earth. What are these ingredients?
Water.
These are the ingredients. So there's two different ways of describing them. Water is included in this, but I'm getting more basic than water. I'm saying what are the atomic ingredients that I need for life? And I want the most basic ones. If you talk about the atoms that are in the human body, for example, there's a lot of calcium and sodium and stuff like that. But you can find life forms that don't need that stuff. But it is really hard to find life forms that don't need these six. Essentially, you can make all the proteins that every form of life has on Earth and all of the DNA that you need just from CHNOPS. The way to remember it is it's Schnapps. You know, you need some Schnapps in order to make life. All right, that's how you can remember it. The P and the S actually are arguable. RNA and there's only a few amino acids that need it. The P and the S are, maybe you could get away with not having it. In that case, it's CHON, Chon, but I kind of like the P. I like Schnapps. So we're going to stick with Schnapps. What we need is Schnapps in order to create the life that is sort of showing up on Earth with the recipes that we're describing. All right, so we're good with that. But that's an interesting selection of atoms, isn't it? It's sort of not all the atoms by any means, and it's, well, we should sort of interrogate a bit. Where do these atoms come from? So here's our pantry, right? We're going to try to get these atoms from our pantry. And I got bad news for you. It's not looking too good to get Schnapps out of this pantry, because the Earth doesn't have a huge concentration of some of the more important ingredients here. It has plenty of oxygen. Well, we're good on the oxygen. But when you start to look at carbon, and when you start to look at nitrogen, and you start to look at phosphorus and sulfur, at least as a whole, the Earth is kind of less and less of a great source. There's plenty of silicon and aluminum, iron, but that's not really what you want for life. In fact, here's what the Earth is made out of. So you can see where our Schnapps come in. Here's our O. Oh, that's good. And do you see any others? Oh, doesn't look so good, right? And so how do we get the rest of the Schnapps? Well, if you don't have it in your pantry, what do? Get delivery, right? So we're going to have a delivery service. The groceries are going to be delivered to us. And how are they delivered? I think you can see, right, through dramatic collisions of things in a period of time in our Earth's history called the Late Heavy Bombardment. So essentially, we start off with a lot of Schnapps, but we're so hot, it all boils away. All of the water and all of the carbon dioxide and methane essentially is given so much energy, so much heat, that the stuff just disappears, dissipates out into the universe, and we're left with the not so great pantry that we have here. So in order to get the stuff back on, well, we have some delivery that happens. And there's two big pieces of delivery that we get. So this is a nice quiz here. Anyone know what this is? This rock?
Meteor.
It's a meteor. What kind of meteor?
Chondrite?
It's a chondrite. Great. It's a carbonaceous chondrite. These things have a pretty high concentration of Schnapps. Sort of surprisingly high concentration of Schnapps, actually. You can go around and find, it's not the huge, biggest necessarily concentration of meteors that are around, but it's certainly a big constituent. And then there's these guys. These are coming from the outer solar system with a lot of the volatile Schnapps. Those are the comets, and that's tail dot, right? That's the first comet I saw. So this is the delivery service, but of course it's coming from where? The grocery store. Right? So where is the grocery store? Where do we get these things, this C, H, N, O, P, and S, to form the life that we want to form? Well, I argue that we get it from here. So what are we looking at here, essentially? This is the interstellar medium. This is the stuff between the stars. Stars are producing things, they're sort of spreading stuff out, and somehow in the medium in here, we're able to gather some of the stuff as the early solar nebula formed. This stuff comes on into the inside, and that's the delivery. We're getting delivery from outside in, essentially what's happening, both with the carbonaceous chondrites and with our comet delivery service in the late heavy bombardment. And if you want to know what the concentration of that stuff is like, it's actually pretty close to the concentration of the solar material. And this is a rather boring chart that explains where all this stuff is in levels of abundance. This is the log of the abundance, so every little step here is 10 times bigger than the previous step. And in fact, you can see here, here's C, here's H, right? Here is O, right? And then N, and then P, and then S. They're all pretty high up on our abundance table here. So the grocery store has quite a bit of this stuff that we can get. And so that's of interest to us to think about, okay, maybe our pantry's not so well stocked, but we can get pretty good delivery from out there. But then maybe the question is, well, why? Why is it so well stocked? Why do we have these particular elements available to us? And so we have to think about how these elements got made in the first place. So I really love this particular periodic table. Have people seen this one? Mm-hmm. This one is new as of 2 years ago. Before 2 years ago, this would have been different. And 2 years ago, an amazing event was seen. Anyone know what this event was?
Gravitational waves.
Gravitational waves from what?
LIGO.
Neutron stars.
Neutron stars, in particular, colliding neutron stars. That was the key thing. Before that, everyone was saying, okay, a lot of this stuff here was produced, all the stuff in the purple was produced in supernova. And then as soon as that event was seen, because we saw an afterglow, this is normal astrophysics speak for these things, because we saw an optical counterpart for this stuff, we could calculate how much of certain elements had to be formed in particular nuclear processes. Long story short, we find that at the rates we're observing this had to have been occurring, most of the purple elements are formed in the collision of neutron stars. And that kind of brings a joy to my heart, because actually neutron stars are what I study. But sort of on the sad note, that has nothing to do with Schnapps. So although this is an amazing sort of production of various interesting things, that's not actually what we're interested in here, because, well, let's look at the Schnapps. There's the C here, there's the H here, there's the N, the O, the P, and the S. So you can see where a lot of this stuff is coming from. It's basically coming from blue, green, yellow, this grayish color. And then the rest of it, well, is not as important for life, at least the recipe that we're talking about. So I thought I'd just show you some examples of how these production mechanisms work. So here's the first production mechanism. This is the origin of the universe. Fascinating subject. I don't have enough time to get into it. But this is where the lightest things, especially the H, comes from. This thing, obviously, is observers' favorite planetary nebulae. It turns out that a lot of the nuclear products, especially the light ones, are coming from these asymptotic giant branch stars that are dredging up new nuclear material from the interiors, coming out, and then that gets expelled in things such as planetary nebulae. So this is an important source for carbon, for example. Most of the carbon that makes you and I up comes from this type of star. This is, which one? Yeah?
SN 1987A, the large
1987A. It's the only one that's ever happened that we could see in our lifetimes, or some of our lifetimes. But still, everyone's favorite supernova until the one that happens in the Milky Way, which is, any day now.
Beetlejuice coming.
Yeah.
I don't know.
I think Ataris.
What about Ed Carina? Maybe that.
Right, Anachronistic. Can't
That's
see
only
that here.
Southern Hemisphere, though. That's no fun.
You should invite Mike Shar up here. He has a catalog of Wolf-Rayet stars. He's convinced one of them is going to go off in his lifetime. So, good one thing. Anyway, 1987A was a Type II supernova. It's what they call a core collapse. Giant star collapses, explodes, pushes stuff out, and you saw that, well, when we go back to my view of what the producers are, that's exploding massive stars. So anything that's in yellow, almost all the oxygen that we're breathing is coming from that. So that's still important, right? Then these are the things down here that are less important. This one is a very interesting one. I love it, but it's not so important for our purposes. This is called cosmic ray spallation. This is where cosmic rays hit other atoms and break them apart, essentially in a fission process. This is how you make sort of the intermediate light elements. It's really easy to make carbon out of nuclear fusion, and helium and hydrogen. Kind of hard to get lithium, beryllium, and boron. Well, you can get it by splitting carbon, and that's essentially how you can get that stuff there. But lithium, beryllium, and boron, not so important for life. So Sorry, it's spallation. Same, we talked about merging neutron stars. There they are. And the last one, which is somewhat important, we do get some of our elements from this. These are the type 1 supernova. This is when you have an overflowing massive star that spirals into a white dwarf, perhaps like the dwarf Novi that was described at the beginning. And eventually that white dwarf becomes too massive to hold up and it explodes in a similar type of supernova, except there's a different amount of chemistry and, well, nuclear physics that goes on to produce a different set of elements. So those are the different producers that we have to thank. All right, so you can see where my extended metaphor is going. We're trying to describe how we get all of the things. So these are the producers, but the question is, well, how sort of special is this recipe? Like, how amazing is it that this is what we have to go on? That the CHNOPS are the things that we need in order to make the life that we're interested in. And I want to argue that it's actually ridiculously strange that these are the producers that we're relying on for life. And the way I'm going to do it is first I'm going to look at all the different stuff that makes up the universe, and I sort of mean stuff in the broadest possible sense. We normally think of stuff as things with mass. And then Einstein came along and said, you know, mass is really a form of energy. And so what we can do is we can do a census of all the energy in the universe and try to say, how much energy do we have in this form, in that form, in the other form? And many of you have known about this pie chart for quite some time, hopefully. That most of the stuff in the universe we are really, really unsure what it is. Dark matter is this stuff that doesn't really interact with us directly except through gravity. That's 25% of the stuff in our universe. Full 70% of the stuff in our universe is this stuff, dark energy. It's only about 20 years known that this was such a huge constituent of our universe. It causes the accelerated expansion of the universe. And we're totally stumped as to what this stuff is. The simplest formation gives us about 70% of the universe made up of this dark energy. So look at how much we don't really know. That's 95%. There's this little sliver of stuff that you and I are made out of, and we kind of all know, isn't that special? But it turns out that we're even weirder than that. If I take this 5% and blow it up, it looks like this. Most of the atoms in the universe are in this thing called hot interstellar gas. This is stuff out in interstellar space never gets to us. It's just out there. That's most of the atoms, like 40%. You know, it's the plurality, right? So it's the person that wins the electoral college, right? It's the most of the gas. No, not most, plurality of the gas. There's also the warm intergalactic gas. You add the two of those up, plus the cold intergalactic gas, you do get a majority. This is stuff that's not in any galaxy. If you think life needs to be delivered to a planet, like it needs to get to the pantry, the delivery service, it's hard to imagine interstellar gas being a big part of this. It's possible, but that's not where most of the stuff that we got came from. In fact, most of the stuff we got did not come from hot gas and galaxy clusters either. We're not in a galaxy cluster. And hot gas and galaxy clusters is between the galaxies anyway. It's also not due to the hot gas in galaxies. Hot gas in galaxies doesn't readily form stars. So what you're looking at is the cold gas in galaxies that form stars. But once you form stars, it usually gets locked up in the star. So it's this little sliver that we like, the cold gas in galaxies. That's what we're looking for. 1.8% of 5% of all that's available. That's how specialty our recipe is, or at least our ingredients are. We can just get deliveries from that. So how do we make this stuff? Well, I kind of alluded to the fact that where we're probably going to want to look is in a kitchen. And the kitchens that we're interested in are these. This is called the Kepler orrery. This is only a small segment of it. These are the planets that were discovered by Kepler, and they're put at the relative sizes and relative distances from their star, right? So you can get the sense for how big and how massive some of the planets are and how quickly they could go around their host star. So this very well could be the full kitchen sort of opportunities that we have if we think that this is the sort of story we need to be telling that life is going to be coming onto the surface of some planet, it's got to be one of these sorts of things. And we're rapidly discovering more and more of them. I'm involved in the TESS collaboration that hopefully will be discovering an order or 2 orders of magnitude more of these things as we go on. So that's all very exciting that these could be the kitchens for life to be forming. When some scientists talk about these kitchens, they start to throw up things like this. And they point out that these Schnapps that we want to have, they're usually in forms of molecules. One of the biggest forms of molecules that people get excited about is water. Let's be honest, water is a real fun one, especially when it's liquid. There's a lot of reasons to think that liquid might be the right thing to have in your ingredients and in your recipes, as we saw with the millerurey experiment. But if you think about the Earth as a planet that has to have water on it, you think about its atmosphere and you think about its temperature as the main things that determine that. And you can say, well, if you're maybe too close, you can't have liquid water because it all boils off into a gas. If you're too far away, you can't have liquid water because it all freezes into a solid, at least on the Earth. So people talk about the habitable zone as being very important for this sort of story. I'm not particularly convinced that this is the best way to think about things, however. Because it is easily possible for you to have a planet that's outside of this zone that has a very thick atmosphere, right? Just as well as it might be very possible for you to have a planet that's inside, on the other side, that might have something called a high albedo, where you reflect a lot of the energy away and cool yourself down. Or even worse, you can have a planet smack dab in the middle, looks like it's perfect, but there's all sorts of things that don't go right, right? There's all sorts of things that can happen that would not allow you, for example, if you have a carbon cycle that's a little bit off, you can completely run away with something way too hot and not have any liquid water whatsoever or the chance for it at all. Question?
Yeah, and there's also tidal heating where you can have a subsurface ocean, like with Enceladus or Europa.
Absolutely. You can have things that have liquid water way outside of this zone. It just has to be in sort of a different scenario. So we should think a little bit more broad-mindedly, I think, than just thinking about planets. On the other hand, we do have our one sample here, and it's kind of a nice one to think about. So these are the kitchens that we're interested in. And so now we have to have the health inspectors come in to try to see whether these kitchens are any good. So what I've done here is given you a sort of survey of the different possible ways you might inspect or discover, really, because we're not even at the point yet where we can really do careful inspection as hard as we're trying, but we can do some discovery. And many of you probably know some of the discovery methods, but there are some obscure ones that I think should get a little bit more cheerleading going on. So this one right now is the leader. This is the best inspection method. This is called the transit method. This is where the planet goes right in front of the star between you and me, and we see a dip in the light of the star, and we say, planet done, inspected, right? There's our first one. So that's a very common one. That's the way that all of the Kepler planets were discovered in the Kepler orrery that I showed. Before transits were popular, this method was popular. This is called the radial velocity method. This is to look at a star that's moving back and forth and seeing some tiny little variation in the spectrum of the star, redshifted and blue shifted, that indicates that the star is moving around, and that can give you some information that there's a planet, right? The star moves a little bit, the planet swings a lot. At some point I want to actually build a barbell that has a tiny planet on one end and a big star on the other. And you can spin it around the center of mass, and the star would spin around slowly, and, well, it would spin around the same speed, but it would spin around in small circles, and an exoplanet would spin around in big circles, if you can imagine that. That's the whole idea. So you can see that tiny little variation in the star, because it's bright, but the exoplanet is the thing that is sort of, doing it. It's the thing that is doing the dance, the other part of the dance. So those are the two most common ones. Now I have to sort of reach a little bit for the other ones. So I have 1, 2, 3, 4 more that are of interest. Perhaps this one is one that people have gotten excited about lately, especially with Gaia. I can animate that one. That was fun. So this is, just imagine looking at this in your telescope for, I don't know, as long as a planetary orbit is. If you can see that star wobble back and forth, you've got yourself some interesting information about the exoplanet. It's sort of the same as this one, but instead of looking at the redshift blue shift, you're actually looking at the movement in the sky. It's called the astrometric wobble. Fantastic word for it. So that's a neat one. This one has been popular with amateurs, in fact, have been very important in this particular method. This is called the microlensing method, where you have a background star and you have a planetary system, and the background star's light is bent because of general theory of relativity, and so there's a magnification of the light in the background star due to a foreground star. That's kind of fun anyway. But if you have planets around the foreground star, that whole signal goes bonkers. And it goes bonkers in a very particular way that you can calculate, and then you can discover exoplanets around that foreground star. So microlensing exoplanets have been very popular. Of course, you need to be right on it. You have to be measuring that light curve right then and there to get that signal so that you can accurately determine whether there's an exoplanet. And some people even think maybe exomoons. Like, that would be really exciting. Right? So that's a fun one, microlensing. This is one that's done by Rebecca Oppenheimer at the museum. This is direct imaging. You use something called a coronagraph to block out the star. You can't tell there's a star there, right? It's blocked out, light's blocked out, but you get the planets. And if you wait long enough, they move around the star. So that's great. But the one that's nearest and dearest to my heart is the way that the first exoplanet ever was discovered. Anyone know how that was? That was the first one discovered. Yeah?
It was a pulsar.
Pulsar planet. Yeah, I love, there's 3 of them actually. There's actually more than 3, but there's the 3 first ones were discovered. And that's done by looking at the pulsars flashing, sort of regularly. And it's an extremely accurate clock. But as with all these things, if there's a planet going around it, it's going to be toggled a little bit in the dance. And an accurate clock that gets moved back and forth, you can tell, right? There are effects, both relativistic and non-relativistic, that you can see as that tiny pulse isn't exactly even, right? It's a little bit shorter, a little bit longer. This gets completely modeled in fantastically wonderful computer programs that I'd love to have time to tell you about, but I do not. But in any case, this is how they first were discovered. And people thought, oh, maybe we'll find lots of pulsar planets. No, we haven't. We found about 5, maybe 6, depending on how you count what the planet is versus what some other compact object might be. So it was the first one, but it doesn't seem to be as fruitful as some of the other methods. So these are our inspectors. This is what we can do. So if we can get all this done, then I say, well, it's kind of interesting what we can produce. And I'd like to end with this slide because I think a lot of times we have a sort of unique and maybe narrow vision of what we think of life as being. We're very focused on human beings and the things that are closest to human beings. When I talk about things that are close to human beings, I'm talking about things like slime molds and cone jellies, like stuff that you would go into an aquarium and look at and think, oh, that's really weird stuff. But that's really, really close to human beings compared to the full diversity of life that exists. This right here was published in Nature 2 years ago. This is the tree of life. And it's organized by DNA comparison. So which organisms have the closest DNA to other organisms? We're up here. This is us. Not only is it us, it's all the stuff that I mentioned. It's anything that has more than one cell, and it's anything that has cell divisions, these tiny little organelles. That's just this one little green slice here. If you go down a little bit along this, there's an entire other domain of life that's called the archaea. These seem to be very old forms of life, and a lot of them can survive in environments that are absolutely preposterous. I have one right here. This is an archaea. It's called Pyriferous. I can never remember these biological names. Let me look it up. This one, this one is called Pyrococcus furiosus. It survives only if the water is above 100 degrees Celsius. So that's a little weird, right? Because we just defined a habitable zone as being, no, so this is hard to fathom. This is another thing. This one, what is this one called? This one is called, it's called Albanella papinjana. Albanella papinjana survives in 135 degrees Celsius water near ocean vents. This is actually even weirder because it's actually one of the eukaryotes. So it's closely related to us, and yet here it is surviving in environments that are completely ridiculous. But a lot of the other archaea, they survive in all sorts of weird environments. They're called extremophiles. They survive in extreme cold or extreme heat or extreme pressure, extreme acid, radiation, and so forth. It's only after you go sort of down this little pipe here that you end up hitting the vast majority of the diversity of life. That's the bacteria. And when I say diversity, I mean look at the DNA and statistically analyze how closely it's related to other forms of DNA. That's where most of the diversity of life on our own planet, in our own kitchen, is. Which is very different from perhaps what we were thinking of when we first think of what we're looking for life, or what the messages or the signals might be. And so I like to end with this because, yeah, we're going to sort of try to go in this direction, but we should be aware that we might be looking for things that are very, very different than what we're expecting. And so that's sort of the hope. That's the dream. That's why we do the studies that we do. And so that's what I have to say. I'm happy to take questions, but thanks very much for having me.
Do you have any brief thoughts on intelligent, conscious life? Is that something you talk about in your class, or is it mostly like the biological side of things?
I do talk about it in my class. I purposely didn't put it in here because once you start adding the question of intelligence, now you have a whole other problem. So I did this first thing on life, and we already had issues because some of you are arguing for computer viruses as being alive, and I'm right there with you. I'm like, yep, I get it. Now let's try to define what intelligence is. Whoo boy, right? Well, you can go through some information arguments, and you can kind of try to say things are, but eventually it comes down to, can you communicate with me? And that's a very centered human thing to say, which is fine. You can go look for things that communicate with me. Great, go do it. But if you're trying to look for the full vastness that could possibly be, that's a very, very narrow line. Things that could possibly communicate with a human being. And it might be that there's stuff around in other parts of this that could do that, and we should think about those things. But it seems to me, and this is my own prejudice, that's very sparse. That's not necessarily the huge variety that is possible. And so, yeah, you can go on and on and on about this. We spend days and days talking about intelligence. So invite me back and I'll do that whole Yeah.
I'm sure this gets asked a lot, but what do you think, I guess, about why we have no evidence of anything yet, other than technological incapacity to detect like something like microbial life, which we'll be able to do with stuff like James Webb on nearby exoplanets at least?
Well, let's start with just the question of, can we detect life on Earth? If you go outside and you dig up some dirt and you DNA sequence that dirt, you will find DNA sequences on here of enormous branches of which there hasn't been a single life form identified. And yet there's the DNA right out there. And so I think part of the problem that we're running into is that we're not exactly sure what the vast possibilities are. And this is also true going all the way out into things like looking at which of these planets are interesting. This is the same problem as here. We're very focused on looking for things like this, but as you pointed out, there's stuff out here that might be interesting. There's stuff that's in here that might be interesting. And it's not clear, because we haven't worked enough to try to figure out where these things are, how we would try to accommodate looking for life in those other situations. We're very focused on our own biosphere, the fact that we have oxygen in our atmosphere, the fact that we have liquid water. And I agree, that stuff is weird. That's amazing. Schnapps, I love it. But it's perhaps worth thinking a little bit about what the other possibilities might be and how we can go about exploring them. And to be honest, it's not being done as much as I think it should be, mostly because I don't think people even know where to begin. We actually need to go back and kind of rethink, what do we mean when we say, what is life, and sort of work forward from that. So I don't think that's a very good answer to your question, but it's kind of getting at the idea that we just need to start thinking a little bit more
I
broadly.
guess to me, detecting something analogous that we can tell what it is, that we already have a good idea of what to look for, even if it's not the representative of the vast majority if it exists. It's much easier to determine.
Yeah,
Or not.
so there's that old story of where do you look for your keys? The drunk guy that goes looking for the keys, they look under the lamppost. And you ask, well, did you drop them under there? And they say, no, I dropped them over there, but the light's over here. Okay, yeah, you can go look there. Maybe they somehow got over there, that's cool. But, we do have to think carefully about how we set up the problems that we're trying to answer. Yeah.
The extreme flight that you were referring to before, would any of those possibly be able to live in the atmosphere of Venus?
Yes. Yeah. The acid level of the atmosphere of Venus is a bit higher than most of the acidophiles that we talk about, but it's not that much higher. So why not? I think a balloon mission to Venus is one of the things that we're missing. Absolutely.
The big problem is keeping it aloft in the clouds, though.
It's a problem, but it's something we should be thinking about trying to do, even if it just stays there for a couple minutes.
I'm talking about the living things. The balloons are no problem. I think we had one.
But they can do it because at 1 bar, does everyone know this? At 1 bar, the atmospheric pressure on the Earth in Venus, do you know what temperature it is at that atmosphere? So 1 bar would be a pretty easy thing to stay aloft at because it's
It's like
pretty
89 degrees Fahrenheit, right?
It's basically the temperature of this room on Venus. The problem is it's sulfuric acid. Not so great for us, but who knows? Maybe there's something that loves sulfuric acid hanging out there. Probably not, multicellular life.